So the following greedy algorithm we were trying to implement in the streaming setting, okay, is that we were trying to maintain maximal matching as it came. And whenever a new edge came, we looked at the edges which it might kick out if we remove the edges which it intersects with and we included it. And we did this if the weight of this edges was more than the weight of the wedges which it kicks out, okay? And we saw that if we do not have this parameter gamma, then this procedure may not give us a good approximation, and that was like this path with 1, 2, 3 up to W, okay? So algorithm was very simple, is that at any point of time, I get a edge in the streaming setting, and if the weight of this edge is more than the edges which it intersects with in the current matching, I kick this out and kick out the edges which it intersects with and add this edge. And the way we argued was that, okay, so we had these few definitions, is that let M star be maximum weight matching, and we will prove that weight of M star is some F gamma weight of M, where M is the matching which we kept. So we say that edge is born if it is either part of M, and edge is killed if it is born but subsequently removed from M by a heavier edge. And then we had this notion of new is murdered or the killed edge, and edge is survivor if it is born and never gets killed. And let S be the survivor edges, and then weight of S was weight of M. And then we define this death trail of an edge. What was the death trail of an edge, if you recall, was that suppose this is an edge in our matching. Look at the edges which it removed when it was inserted, and look at those edges when they were inserted, what they removed, so on and so forth. So, right? So C0 was E, C1 was edges that were killed by E, C2 was edges like F in C1 and they kill. So this kind of makes a kind of tree structure. And so this is how we define CI. And we proved last time that, look, if you look at the weight of any CI minus 1, it must be 1 plus gamma times the weight of edges at the next step, okay? Because I mean, and we argue that, look, each item here is more than 1 plus gamma times something like, so basically each of these pays 1 plus gamma times some, like, so basically it's a partition of edges. So edges in CI minus 1 partitions the edges in CI, and for each part, this individual pays 1 plus gamma times more than the weight here. And that is how we showed that for all I greater than equal to 0, weight of CI is greater than weight of CI, 1 plus gamma times weight of CI plus 1. And then we sum this up for all this, and then we got this nice inequality that the weight, look at our survivor edge, or look at the edge which is part of our matching, and look at the set of edges which is in its death trail, then its weight is what do you call, at least gamma times weight of this death trail, okay? So this is what we showed last time, and then we were trying to argue the weight of M star in terms of matching which we had. And so the way we did was that, look, basically we had that the reason O was never included in M, okay? So why O was, so we tried to, in some sense, try to, let's say, map the matching edges of M star to the matching, to this death trail. So how, so just to be on the same page, so suppose M star is O1, O2, dot, 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 some OL, okay? And here's my death trail, okay? So first of all, some of these edges are part of M also. So we assign these edges, matching edges to, so some of the edges of M, some edges are part of M also. So this is one kind of edges. The other edges are like, suppose I have some O, which is say U comma V, okay? Now, what could have happened? So this edge U comma V was never included in M. This could be the one case. And in this case, we said, well, then why it was not included? Because look at the edges which were present in the M at that point of time. M, when UV came, okay, let us see M when UV came. There could be two edges, some say E1 and some is E2, such that O intersects with E1 and E2. And what extra property does it satisfy? Well, weight of O is less than equal to 1 plus gamma times weight of E1 plus weight of E2. This property is satisfied. This is why I did not include him. Then what I do, okay, fine. Then I said, okay, let's charge. So suppose E1 is here and maybe E2 is maybe in this tree itself or somewhere. I'm going to charge to say the weight which is proportional to that edge. What is the meaning of that? So I'm going to charge to E1 the following. So E1 we will charge weight of O times weight of E1, weight of E1 plus weight of E2, and to E2 we will charge weight of O times weight of E2 divided by weight of E1 plus weight of E2. Okay, this is what we are going to charge. Now the invariant which it is something which is interesting, is that look at what this value is. Well, this value is less than equal to, if I look at 1 plus gamma times weight of E1 plus weight of E2 times weight of E1 divided by weight of E1 plus weight of E2, right? Now, this and this will get cancelled, and all we will get is this, right? So the edge O charges to maybe this vertex and charges to this vertex. How much quantity it charges? It charges 1 plus gamma times weight of E1. This is the charge which gives it. What is the charge which it will give it? 1 plus gamma times weight of E2. Okay, this is a charge which it can give. Now, let's ask ourselves, how much charge will an edge receive? How much charge can an edge receive? How many times a charge can it receive? So look at any edge. Look at any edge in TE. Okay, any edge in TE. Okay, right? This edge can intersect at most two edges of M star, right? So no person here will have weight more than 2 times this, right? So this is the charge accumulation anybody has. Now, what did we do at the end to get an approximation algorithm? We said, okay, so now what is happening, that for every edge, right, for every edge E1, right, look, weight of O is less than equal to this times this, right? And now if I had to count I have to relate, say, M star and M. So what did we do last time? To relate M star and M. What did we do? We said, okay, let us count all the charges. Okay, this is what we did. Let us count all the charges. So now we have a different trees. Right? E1, E2, let's say EQ. Okay, these are survivor edges. Okay, okay. So notice, and so this was for the case when E was never included in M. And what we did, how did we define the charges? Well, if an edge O was included, then charge him. Okay. So suppose here is a guy charged because of inclusion. Question number 1. Will this be ever be charged by any other edge of M star? Can this edge be charged by any other edge in M star? Let's ask ourselves. Will it be?
No, because M star is a matching and this edge doesn't intersect with any other edge of M star.
Exactly. Correct. So this is why what happens is that no guy gets more than 2 charges. No guy gets more than 2 charges. Okay? No guy gets more than 2 charges. Okay? Now notice that what happens for a particular edge. Okay? If for a particular edge, I'm going to actually, so the way we are going to count everything, we are going to not worry about anybody. And so now suppose I had an edge O included, right? Included. Then what happens? It was included in M some point of time. Then actually I'm going to charge for him 1 plus gamma times weight of that O from here. In fact, because we are going to be blind about this, we're actually going to charge him 2 times this. Right? But that's perfectly fine. Nobody charged. Okay. Now look at an edge O, which was never included. Then I'm going to charge 2 people. Charging here, charging here. How much am I going to charge? How much did I give him weight? Well, at one place, I give him weight of O, weight of 1 plus weight of E2. Weight of O, weight of E1 plus weight of E2. So although though this guy is mapped to 2 places, but look, if I add the weight of both edges, what happens? Then I know that the weight of O is less than equal to, if I, no, what did I do? Weight of E1, weight of E2, right? So if I sum this up, right? So if I sum these charges, what I'm going to get? Well, I'm going to get, if I sum these charges, how much I'm going to get? Well, I'm going to get weight E1 plus weight E2, right? And this is weight O times weight E1 plus weight O times weight E2. This is what we are going to get, which is exactly equal to weight O, right? So weight of O is equal to this. Now, what do we know about this? And this, because of our invariant, what is this? This is less than equal to 1 plus gamma times weight of E1. This is the first term. And another one is 1 plus gamma times weight of E2, right? So I'm actually, this is what, so for this guy, when I count twice, I'm taking care of all these guys. Okay, so this is why if you count charges on everybody here, right, just charges, then what are we going to get? We are going to get weight of m star in terms of charges. So this is why we said last time, what is a weight of m star? Well, weight of m star is some edges which is part of the matching. Some edges which are part of the matching. So let's say, let's say some edges which are edges of m stars that are part of m, plus everybody else gets charged. Now notice, if an edge here, so look, if something is part of m, those edges are anyway charged exactly once, right? Exactly once. So if I multiply everybody here just 2 times something, then I'm very happy. So basically what it amounts to is that, so edges of m star that are part of m not part of m plus charge to an edge in TE for some E in M, right? Okay. So this is like, this contributes, say, something like weight of M1, okay, which is fine. And not part of M, well, those guys could be charged twice their weight, because like they are not part of M, but they could be charged by 2 more people from, can it be charged by 2 more people? So an edge here, E1, it can be charged by 2 people, right? The survivor edges, right? So the question is, do I need to count for those edges weight of E1? Should I count or should I not count? Look, I'm interested in upper bounding weight of M star. Yes, it could be 2 survivor and 2 edges could be, but I should only count the charges, because that is what is the upper bound on M star. So even though the M is not part of M, there could be 2 edges of M star that could be providing charge to them. So now you write E in M minus M1 2 times 1 plus gamma times weight of E. Okay, that is fine. Plus summation E in M. Okay, summation E in M. E in M, say X in TE, 1 plus 2 times 1 plus gamma times weight of E, weight of X. Right? This is it. Now, I mean, this is a good case for us. So I can write this is 2 into 1 plus gamma times summation E in M, weight of E. Plus, what is this quantity? Well, this is nothing but I can write 2 into 1 plus gamma summation E in M weight of TE, right? Which is less than equal to 2 into 1 plus gamma, right? Weight of M plus 2 into 1 plus gamma. And what is E in M weight of TE? Well, we had an upper bound of on these quantity, right? Weight of TE is less than the corresponding weight of E divided by gamma. Okay, so this is weight of E divided by gamma E in M. So from here, if you look, what did we get? So this is 2 1 plus gamma weight of M plus 2 into 1 plus gamma by gamma into weight of M. So basically what we will get is 2 into 1 plus gamma, 2 into 1 plus gamma divided by gamma times weight of M. So if I substitute gamma equal to 1, what am I getting? Well, if I substitute gamma equal to 1, I should get something. I don't know what I'm getting. 4 plus, right, 8. Am I right? So if you put gamma equal to 1, we can say this is 8 equal to 8 weighting. Okay. But basically, I mean, think of this as like 2 into 1 plus x plus 2 into 1 plus x divided by x and minimize x. Okay, you should get some value. Okay, I just put 1. But this is not the right way of, this is not a complete correct analysis. Okay, why it is not a complete correct analysis is something we can do something slightly better than whatever I wrote here. Okay, so let me say why we can do slightly better. So let's look at a particular tree. Okay, I will ensure, so this is my goal, ensure by some charge distribution that each node in death trail that is not root has at most 1 charge. Okay, so what you do is very simple. Look, so you pick up, say, you have 3 guys, U1, U2, and U3. Okay, you have U1, U2, U3. Just 1 second. Where is my lecture notes? Yeah. Okay. So, okay. And so these are distinct U1, U2, and U3. Okay. So suppose if E equal to, say, U1 comma V got charged by, say, O equal to U2 comma V. Okay. So suppose this edge E you charge to U2 comma V. And what happens? E is subsequently gets killed. Right? E is subsequently gets killed by some E prime here. Right? But what is the property of E prime? Right? So E prime is going to be something like U3 comma V. Right? It could be any endpoint, but let's just say E prime is U3 comma V. Now what will we do? Transfer the charge to E prime. Now, what is happening? So you must understand what is happening. Is that, look, why did I kill E prime? Well, I killed E prime. Like, why did I kill E prime? Like, or why did I introduce E? So, well, I killed E and other guy because E prime was intersecting with him. Okay. Now, if E has two charges, it means there are two edges of M star which are incident on me. Right? That is why I have got two charges on me. Now, I know that at least if new E prime has got, if I have two charges, only then I have an issue. If I have at most one charge, I don't care. But suppose if I have a two charges, then why, like, what happens when some other E prime comes? Well, some other E prime comes and kills me, then it must be intersecting with one of my neighbors. And if it is intersects one of my neighbor, I have two charges. I pass on charges to him. That's it. Now, so this is my charge throwing scheme, like moving or redistribution of charges. So now, because of this, what happens that nobody has two charges except maybe the root. Okay. Okay. So this implies this redistribution of charges makes sure that each node has only one charge. Okay? Okay. Then, if I go back to my computation, what will happen? Well, now I can write down with everything that weight of M star is less than equal to 2 times 1 plus gamma times weight of M. And now, for the weight of TE, all I can say, it is like 1 plus gamma times summation E in M weight of TE, right? And now I will apply the lemma from previously and get this is equal to weight of M. Okay. Okay, this is what we get. Okay, and now this is where my problem is. Okay, and this is this I checked several times. So so please, I might be may not say something correct. So if this is the place where I might be making a mistake. So now I said that okay, what is my goal? I would like, this is my gamma is my factor of approximation in some sense. Okay, so this is what gives me the factor of approximation. What should be the weight of the newly introduced edge? By what factor should it increase from the edges it intersects that I achieve this? So I thought, okay, if this is the case, let me minimize gamma for this function. Okay, and so I get gamma equal to say √1/3. Okay, and if I do that, then I get the approximation factor becomes like 2 plus 1 plus √1/3 plus 1 plus 1/√3, 1/√3 or whatever, right? Okay, if you do this, this is exactly equal to 5.464. Okay. Okay, and then I really did not understand what are these algorithms were doing. Okay. Okay. So this is what this claims. Then there was a paper with 5.828, then there was a paper with 5.585. I really did not understand what were these algorithms doing. You understand my point? So all I'm saying that, so the paper which I was trying to teach you, they say that, okay, they already substitute gamma equal to 1 here, and that is what they work with. So if I substitute gamma equal to 1 in my equation, right, I will get 6, if I understand correctly. Right? If I substitute, say, gamma equal to 1, that will imply gamma equal to 1. So 1 plus 1, 2, 2 into 2, 4, and 1 plus 1, 2. So this is like, if I substitute, it gives 6 approximation. Right? But if I take gamma equal to, say, √1/3, I actually get 5.464 approximation. And I couldn't find mistake in this. Okay. So do you people see any mistake? Like there's absolutely no problem till here. Like this is an equality which you will get even from like if you just follow the kind of steps they do in their algorithm. But then either I'm missing something or they miss something. Okay. So this actually will give you 5.464 approximation. So the reason why I started with gamma is because I thought that it shouldn't come as a magic. So I was just trying to figure out that is the gamma being 1 is a magic number, or is it something, I mean, how could someone get it? But when I tried with gamma, I get a better approximation than what is being claimed. So, okay. So first, I mean, okay. So this is something which for us to figure out whether I did something wrong or something right. Okay, so this is one idea which is used quite a lot in matching. Okay, so the idea was apply some charging scheme. Okay, so now the second idea which is being used quite a lot. So this is the second algorithm which I'll give now. Okay, this is like 4 plus epsilon approximation algorithm. And this is very cool algorithm in the following sense, is that here your stream, right? And you are interested in computing weighted matching. You actually solve your problem on unweighted matching over several streams. And then take all these solution and merge them to get a good approximation for weighted matching. Okay? Okay. So what do you think should be a good strategy to do these things? Any idea? So is the overall strategy clear? So I'm coming in the streams with some weights. I want to create several instances of unweighted matching. And for unweighted matching, we have very simple greedy algorithm, right? Like, well, like usually just compute them, okay? And once we compute them, how do we go about? And then we'll combine them to get a very good approximation for this, for the weighted matching in general. Okay. So this is something which is quite, I think now a very common stream. Like you partition, or actually partition is the wrong terminology. This is a slightly different. It's not partition. We will make several graphs. This is okay. Based on edge weights, but several cannot be more than polylog n, okay? Because that is the amount of space we have. So what we'll create is like EI is E in E. Now, what do you think weight of EI should be? So let's fix an epsilon greater than 0. Okay, so this is my EIs, and what is my GI is V comma EI, and I compute this from I equal to 0. Okay, and I will tell you till where will we compute. Okay, and say W equal to max of weight of E in EG. Okay, so I'm going to compute this is like log 1 plus epsilon times W. Okay, okay, so that many. So what is the property of GIs? Can you say any property of GIs? So for example, what can we say about G0, G1, G2, and say this is Q, GQ. Is there some relation between G0 and G1, G1 and G2, so on and so forth?
Subgraph inclusions.
Which way?
So, well, in each round you increase the weights.
Exactly. So G0 contains G1 because this is basically G, right? Because what is, if I put I equal to 0, what will I get?
No, it's the other way, I think. Yeah?
No. Epsilon is a fixed quantity, right? So, like all edges which has more weight, right? So it should be this way. This is correct. So GQ excludes lots of edges, right? G0 will include all weight. So suppose weights are like at least 1, something. Okay. Yeah. So yeah. So let's also assume that weight of EI is greater than or equal to 1. Otherwise, we'll have to do something. Okay. So why I say, because look at G0. It is 1 plus epsilon to the power 0, which means that weight of EI is at least 1, which is the criteria. So you will get G0 equal to G. What is G? All the edges whose weight are at least 1 plus epsilon. So you're forgetting some edges. G2, 1 plus epsilon to the power whole square. So it is slightly larger weight. So you're basically staggering the edges based on this. But so this is what we're going to do. So these are the graphs where it is inclusion wise. So G0 contains everything. G1 contains some edges with slightly higher weight. G2 contains edges of even higher weight, so on and so forth. And GQ contains all the weights which has like very high. Okay. So now basically, now notice that I can, based on this, I can compute. Okay. So we can compute a cardinality maximum matching in each GI parallelly. What I mean by this, okay? So now what I'm going to do, so we'll compute C0, C1, C2, CQ. And what will be the procedure? This is like a greedy maximal matching, okay? So what I mean by greedy maximum matching? Well, you are keeping some edges, an edge comes, okay? Check its weight. Okay, is it greater than or equal to 1 plus epsilon? So is it greater than or equal to 1? Yes. Then I check whether I can add it here. I'm not even talking about weights at this point. Can I add this edge? Well, if this does not intersect with the edges I have already selected, I will add it. Okay, great. Now, same with C1. Like there will be some I. After that, the weight of that I is too small to be considered. Okay. Too large to be considered in this particular graph. So this is what I mean by that. We will construct this maximal matching in parallel for each of these graph G1 to G0 to GQ, and let's call them C0, C2 to CQ, and then we will do something. So in particular, so if I have to write algorithm, okay, so we will say first EI is E in E, weight of E is greater than or equal to 1 plus epsilon times I, and GI equal to V comma EI, okay, I going from 0 to log 1 plus epsilon times W. Secondly, in parallel, compute an alpha approximation, okay, approximation for maximum matching CI of GI. We, at this point of time, we only know factor half approximation. Okay. And third, now it's a combination step. Okay. It's a combination step. So now how am I going to compute M phi? What should we do? How do you think we should give priority to? Which edges should get more priority to be included in my maximum matching? Look, C0, like look at the last matching, like CQ, right? Look at the matching CQ, right? Hopefully, notice that CQ is a maximal matching, on heaviest edges in some sense, in heaviest edges, right? And so on and so forth. So when I'm computing this M matching, I'm going to give more priority to edges which are present in the top guys, and then the next top guys, so on and so forth, while constructing. Okay, and I'm just going to construct this maximal matching, but I'm going to construct this maximal matching in a very, like in a particular way rather than greedily. Okay, so but this is also kind of greedy only. So what we will do for I equal to log 1 plus epsilon W, which we have called, say, which we have called Q to 1, okay? Let E be in Ci, and let M be M union EI if both endpoints are unweighted, are unmatched. Okay, that's it. This is my end of my algorithm. So what is my algorithm I'm doing? So notice that M contains everything from CQ, right? Because what I'm going to do, look at every edge in my last CQ, okay? And what is my, look, this is a maximal matching or maximum matching, whatever, this gets included. When I'm next time I'm going over all the edges which I have computed in my matching, and I say, look, can I add it to you? Well, no, because you have both endpoints. If I could add this edge to this without, yes?
I have a question.
Yes?
Can you go back to the definition of CQ? Because I'm a bit lost now. So EI, you say if the weight is, okay, no, okay, never mind, sorry. I thought, yeah, right, okay.
So let's go back here, right? So basically think of this GQ, I have put a threshold of what is the weights on edges we should have in this graph, right? So when an edge arrives, you know what is its weight, right? Now it means you know which all graphs does it belong to, right? Now what I do, I'm partially constructing a maximal matching in each of these graphs. I say, can I go and add to you C0? Yes, if I can. If it, right? Yes. C1, can I add to you? If it can be added, just add it. So on and so forth. We completely forget the weights of edges. Okay?
Yeah,
right?
okay. Yeah,
That's it.
So, yeah.
So just that larger the index, heavier weights it has. So now when I'm constructing M, I'm giving more priority to heavier weight because we are interested in weighted maximum matching. Okay? So it's like, okay, I only go to a lower weight edges or edge weights if I cannot get a maximal matching from the top set of edges. So this is what this loop is doing. So I'm going from higher weight CI, which we have stored. So we have stored CQ, CQ minus 1, and C0. I say, definitely, okay, can I add all, so I go one by one in this edges, and I say, can I add it to my current matching? Unweighted matching. And when can I do that? If both endpoints do not intersect with, they do not intersect with any matching edges, then I just add it. Okay, fine. So I will have some MQ in the beginning, then I will have some MQ minus 1, and I will have finally M0. But what is the property here? MQ is contained inside MQ minus 1. MQ minus 1 will be contained inside MQ minus 2, like after we have done first step. Okay, so on and so forth. This is what it is, right? Because I'm never destroying my matching. I'm going from top to bottom. Whatever matching I have at this point of time, I take my current set of edges and I check, hey, can I add to you? If I can, I add. Otherwise, I go to the next set of matching. So basically, think of this way, is that I have collected roughly, if you notice, in the worst case, I would have collected how much? N by 2 times log, or say, Q edges. So this much edges be kept. Okay. Like I'm doing in a very nice way, but after this, I could have just run a maximum matching algorithm because I have a small, if I had a small space maximum weight matching algorithm, or I would have just computed a maximum weight matching on this set of edges in exponential time. But I'm not doing any of these things. Even the approximation algorithm itself is a good, like a greedy maximal algorithm is good enough for our purposes. Okay. So we have stored this n by 2 q edges, which are nothing but matching this CQ to C0. With help of that, we are creating a matching M. And we have to prove that this matching is very good with respect to the maximum matching and so on and so forth. Okay? Okay. So somehow the basic question is how we relate cardinality to max weight matching. Okay. Okay. So let's first prove. Let's define Mi is M intersection EI, and I'm going to define Mi star is M star intersection EI, and M star is an optimal matching. Okay. Okay. So the lemma which we'll prove is 2. For each I between 0 and log 1 plus epsilon W, we have that Mi is 2 times, okay, let's say Mi star. Okay? Okay. Now, this is what I want to show. Okay? So, if we had a better approximation in the unweighted setting, say alpha, then we would have got here alpha. So, let's talk in terms of alpha. What can we say about CI? Well, and suppose opt-I is the best unweighted matching in GI. Okay. So what is CI? Is at least 1 by alpha times opt-I, because it was an alpha approximation. And if we apply our greedy algorithm, that is definitely half times opt-I, right? Okay. But opt-I is at least, look, mi star as a matching is at least this, right? Okay. Okay. So if we just substitute alpha equal to half, no, say alpha equal to 2, okay, then this tells us that this is like half times mi star. So this is fine. So Ci is definitely, no, like in terms of cardinality, is at least half time mi star. Okay. But what about mi? What about mi and Ci? I claim that mi is greater than at least half times Ci. Why? How are we constructing this matching here? Let's see. We add edges, and at any point of time, okay, look at your Ci, okay, and look at your mi, okay. Now, I want to say that mi is at least half times Ci. Well, what am I doing? Look at any edge of Ci, okay, at any edge of Ci, okay. And why is this edge not included in mi? Because it intersects with some edge of mi. Okay. So each edge in Ci can kick out two edges, at most two edges of mi. Right? So if the size of mi is less than 2 times Ci, then there is an edge in Ci, right, which does not intersect with any edge of mi, then we should have added it. So this implies that mi is at least 2 times Ci. The cardinality of mi is at least 2 times Ci. So what does this implies? No. What did I write? Each edge in Ci can kick out at most 2 edges. Oh, sorry. Right? So if Ci is more than this, then you could have added an edge from Ci to this, which implies that mi is at least Ci divided by 2. So that's it. So this implies, now if I combine all this, what I'm getting, mi is at least half times Ci, which is at least 1 over alpha times mi star. So it is 1 over 2 times alpha mi star. That's it. So for alpha equal to 2, what are we able to show? Mi is greater than or equal to 1 by 4 times mi star. Okay, size wise. But we are not interested in size wise. Okay. Now I will tell you some very interesting property of this matching. Okay. So I want to say that there is a mapping sigma from m star to m such that for each E in M, sigma inverse of E is less than or equal to 2 times alpha. Okay, that's the first property A. And the B, what I want to show is that for any E in M star weight of E prime is less than equal to 1 plus epsilon times weight of the person whom he is matched to. Suppose I'm able to show this lemma. Do we have a proof of whatever we wanted? Well, look at your weight of M star, right? Weight of M star, I can write it down, is summation E. Suppose I prove this lemma. Then I can write it down, E in M star, weight of E. And what do I know about these things? Well, I can write down this is less than equal to E in M star. And what is the property of weight of E? Is at most 1 plus epsilon times the edge which it is mapped to. Okay. So it is weight of sigma E. Great. Now this is less than equal to, okay, or rather equal to, okay. Now I want to interchange this summation. Okay, so I write down, say, E tilde in M. Okay, so I'm going over rather, okay, E tilde in M, summing over, right, E in M star, sigma of E is equal to E tilde, weight of 1 plus epsilon. Okay, right? So I take out rather 1 plus epsilon times weight of E tilde. Right? This is what I can say. Now, what is the property of the matching, property of this mapping? The first property of this mapping, that no edge is mapped by more than 2 alpha people. Okay, which implies that this quantity is less than equal to E tilde in M 1 plus epsilon 2 alpha times weight of E tilde, which is equal to 1 plus epsilon times 2 alpha times weight of M. Well, so if alpha equal to 2, because that is what algorithm we have, what will we get? We'll get 4 into 4 epsilon times weight of M prime algorithm, right? So given epsilon, I could choose epsilon E prime equal to epsilon over 4 and apply this algorithm. Apply this algorithm with epsilon prime, okay? And we are done. So the algorithm is simple. What is not yet simple is how do we prove this claim? Okay, so now let's try to prove. So what do you think the proof for this will be? How do we map this? How do we construct this mapping? How do we construct this mapping sigma from M star to M? Given E in M star, where do we map? This is where we will use the first property. So where do you think we should be mapping him? So I first check what is the largest I such that weight of E is okay, or rather, what is the largest I such that E is in mi star, right? So we constructed these mi's, right? The intersection. How did we construct these mi stars? So if you recall, this is our algorithm. Okay, so we defined mi star is the optimum matching intersection ei, right? So basically, look at this edge and look at the which is the largest graph which it belongs to. So okay, so I'm going to map E in mi star to some edge f in mi. Okay. Now, which edge in fi? Well, map E to an arbitrary edge f in mi, okay, such that strictly less than 2 alpha edges are mapped to f. Now, question is, why such f exists? Well, what did we prove? We proved that mi is greater than or equal to 1 over 2 times alpha mi star as a cardinality, which implies that mi star is less than or equal to 2 times alpha times mi. So it means that I can distribute the edges of mi star to edges in mi, because the cardinality of mi is at least 2 alpha times mi star, right? So which implies that no edge will be more heavier than 2 alpha times, right? So because of the construction, what we have been able to show that for all E in M, cardinality of sigma inverse of E is less than or equal to 2 alpha. What else can we say about this? Look at your E prime in M star, right? It was mapped to the largest I, right? So what I know about this, weight of E prime is less than or equal to 1 plus epsilon times I and less than or equal to 1 plus epsilon times 1 plus I, right? Now, this is where our objective helps. Well, but what is the property of F? F. Well, weight of F is also greater than or equal to 1 plus epsilon times I. Otherwise, it cannot belong to the GIth graph, right? Which implies, now if I take these two inequalities, what I can write? Well, then weight of E prime is less than or equal to 1 plus epsilon times 1 plus I, which is equal to 1 plus epsilon times 1 plus epsilon I, which is less than or equal to 1 plus epsilon times weight of F, right? And which is equal to 1 plus epsilon times weight of E prime, right? So we have been able to show this. So basically the idea is very simple, is that look, I have constructed these matchings from heavier to lower, and I have given more preference to heavier edges than to the lower edges, lower weight edges. And I try, so think of this way, is that the edges in the top weight graph is like more or less has very high weight. So even if I pick someone else there, they will kind of compensate with each other. And that is what is happening here. So in some sense, like ideally one would have liked to partition these edges based on these weights, some weight function, like between this and this, find a good matching there, and then try to combine, because then if you find a matching in that, you know that all the edge weights are like something very same, so you can treat them like a one. But that strategy doesn't work. But this strategy is essentially exactly doing that by filtering out things in a nicer manner. Okay, so this is why what we are able to get is 4 plus epsilon approximation. Okay. Any question? Okay. So if there's no question, then let me, okay, I will try to, okay. So, okay, so let's try. I'm going to change a track for a minute, okay, and do a minimum vertex cover, okay, just to give you a feeling of, or rather, okay. So let's see. I don't know what to say. Okay. Okay, so rather, okay, I think this will be a bit more easier to understand. So suppose I want to do vertex cover, and this time also my objective is to do factor 2 approximation. Okay. And so input is G, V, E, and I have a weight function W from V to say R positive. Okay. And I want to find what I want to output a set S subset of V so that weight of S is less than or equal to 2 times opt vertex cover. Okay. Optimum size vertex cover. This is what I want to do. So cardinality vertex cover was very easy. We find a matching edge, delete it, and so on and so forth. How will we go about doing this? So this is like what is called a local ratio technique in approximation. Okay, so think of this way, that you want to buy, so you have a grocery shop, okay, and you want to buy a product, say want to buy one product, okay, but you don't have money. I mean, it's a very simplistic, okay, you do not have money to pay for all, like for pay in total. So what you decide to do is that you pay in piece by piece. What I mean by this, piece by piece, like you do some down payment now, okay, and the shopkeeper in turn, okay, like does not want to be, shopkeeper doesn't want to be bothered by keeping all down payments, okay. So what should he do? What is a simple way to adopt some strategy, okay, to remember how much one needs to pay? Right? What I can do, so if I have a product P, okay, then suppose it has a weight or say cost of P in the beginning. What should I do now? Rather than remembering cost of something, I will, okay, so you paid me some money, okay, then I will, next time I will just not remember this, but I will remember, I will just change new cost P. What is the new cost P? Is basically cost P minus down payment. Right? So each time my new cost will be whatever the down payment, like cost P minus again the down payment. So think of this way is like, so cost of this product is basically sum of costs until it become 0. Okay. So this is the kind of strategy we would like to employ in this. So what we like to do is that given a weight function, okay, I will say, well, let's decompose this weight function into W1 plus W1 bar. Okay. So it's like, think of W1 is like my down payment, and W1 bar is like, it will be like, let's say, remaining. Okay. Then you further write down this into, okay, you further write down this into, say, W2 plus W2 bar, and so on and so forth. Finally, you can write W as W1, W2, sum WL, and what the property of WL will be? It will be all 0 weight, okay, in general. So now if you have all 0 weight, many problems are easy to solve, because all it boils down to is like a feasibility question, or yeah, so it all boils down to some sort of feasibility question, some kind of feasibility question, which are easier than, let's say, optimization question. Okay. So for example, for vertex cover, here's my weight function. I will try to do, okay, like first time. So what I'm going to do, so if you look at Klein-Bertardo, this is what it calls pricing mechanism or something. So if you have you have edge u comma v in G, okay, and suppose both wu comma wv is greater than 0, otherwise do nothing. So my weight function will be w1 of x is equal to wx minus minimum of wu comma wv, and it will be wx, and this is what I'm going to do if x is going to be one of this edge, or if x is not in the set u comma v, right? So this is my w1x. Okay, so my objective is that look at w1 of x. I have reduced the weight. Okay, I have reduced the weight. So w1 of x is like wx minus minimum of w1 comma wv and wx. Okay, so I have subtracted some weight from u and v, and I have what do you call? I have kept the weight of other guys same. So if I write w1 bar, which is nothing but w minus w1, what is this weight function? Well, if you look at this weight function, then this weight function is nothing but, what is this weight function? W minus w1 bar. It gives, look at this edge uv. Okay, look at this edge uv. Okay, what do you know about one of u comma v? So suppose wu is less than wv. So what is w minus w? Suppose wu is less than wv. So for what will the weight of weight of u? It will be 0. And what will be weight of this? It will be weight of this is going to be wu, and weight of all other vertices is going to be 0. Okay. Okay. And what will be the weight w1 bar? Well, it is w minus w1. Right? So this is by which I have manage to reduce my weight. So let's see, what will be W1 bar? Yeah, so this is what W1 bar is, okay? And this is W1 of X is, okay? So now notice that I have been able to write my weight function W as W1 plus W1 bar, okay? And suppose we are able to solve the problem on W1 recursively. And we get, say, factor 2 approximation. Okay. Let's, okay. This is what we do, okay. No, no, no. Did I do something correctly? No, no, that's not what it is. Okay. The property of W1 is that in W1, weight of U is 0, W1 of U is 0, W1 of V is W of V minus WU, and W1 of X equal to WV. Okay. Okay. But what is this W minus W1 bar? Well, this is equal to, this will be equal to, it is W, so definitely in W1 bar, everybody else gets 0, but these guys get slightly different weights. Okay, let's see what weights they get. So it is W minus W1. Well, so for U, in W1, W1 U is equal to 0. So W minus W1, this is equal to, this is W1 bar of U is equal to weight of U. And W1 bar of V is equal to what? Well, it is W minus W1. So it is going to be equal to weight of V minus weight of U minus weight of V, because this is what W1 gives. So this is going to be equal to WU minus WV. So what is this? Equal to weight of U. So even this guy gets its weight of U. Okay. So do you see very interesting property of the kind of weight function we define? Now suppose you got a factor 2 approximation. Okay. I claim that, you know, that is simultaneously a factor 2, simultaneously a feasible solution with respect to both W1 and W1 bar. Okay. W1 bar, W1 by definition, but why it cannot, look at W1 bar. W1 bar, the only reason it may not be a feasible solution, well, because why it will not be a feasible solution? The graph remains the same. So it is a feasible solution to start with. Okay. So definitely feasible solution. So that is by definition of G. Okay. Now the problem, the point is that look at W1 bar. I claim that the solution what you have, like S, is a feasible solution with respect to say W1 and weight of S, okay, and W1 of S is weight is 2 times opt 1 of say, how do I say, with respect to this new weight function, okay? Don't worry. 2 times opt, say, weight 1, comma G. Now, what can you say with respect to W1 bar of S? I claim that this is also 2 times opt W1 bar, comma G. Suppose we are able to show this. Then what happens? What is the property of S? Well, look at the weight of S. It is equal to weight 1 of S, which is equal to weight 1 bar of S, which is less than equal to, say, what is weight 1 of S? Well, weight 1 of say S is like 2 times opt weight 1 comma Z, and this is like 2 times opt weight 2 bar comma G. Okay, so this is like 2 times opt of weight 1 comma G, opt of weight 2 bar comma G. Okay, but now can we say anything at this point of time? Okay, so the way we will construct this weight function, okay, we will be able to conclude from here that this is less than equal to 2 times a opt of weight of G. Okay, so this is the kind of strategy we would like to do, and it is not very hard, but we will do a concrete example with concrete weight functions to give you some intuition of local ratio theorem. But the best way to view this is a recursive procedure who decomposes my weight function into simpler weight functions till I get a weight function which is like a very simple weight function that I can solve my problem very trivially. Like, for example, here, recall that if all weight functions, like all the edges, like if every edge has one endpoint with weight 0, then if you pick up those solutions, then what is the property? That's definitely a vertex cover of weight 0. And you cannot get more optimum than that because every weight is 0 or something more, right? And in this process, what am I achieving in W1 and like in W1? Well, I have some weight function which I reduced. So it is like W1 bar, W1 plus W1 bar. So keep W1 bar separately because it's only local object. And what is a great property of W1 bar? Well, what is an optimum solution of W1 bar? Well, optimum solution of W1 bar, because both weights are same, it is just equal to W1 of one of these guys, right? So the total cost here, like total cost of W1, which will be, if I take here, is at most this guy could be picking both endpoints. But for this weight function, I know any optimum solution has to have a weight at least WU. Or in other words, think of this way that look at any optimum solution. Look, either he has to pick U and V, whichever vertex it picks, it has to pay at least minimum of WU or WV. This much everybody has to pay. If this is what I have to pay anyway, so let's reduce that cost from these two vertices, and let's compute an algorithm with respect to reduced weight function. If I find a solution, then I know that if it then I know that if I add back weights to these guys, well, I could have only added the WU, which I anyway have to pay, maybe 2 times because both vertices are in my recursive solution. So I pay twice. But if I pay only once, then I'm great, right? But that I anyway needed to pay. So I'm paying twice more. So this is the strategy which we will apply. And to get this 2 plus epsilon approximation, we will apply this strategy, but in streaming, okay? And the algorithm is basically similar to 6 plus epsilon approximation, but the proof is very, very different, and it was kind of a nice breakthrough in this. But I think today this is all that I wanted to tell you, to keep something a little bit about local ratio. So if you have not seen it before, then please have a look at local ratio tricks and techniques. That you can find it at what do you call, if you do Google search or something. Okay, so I think this is all that I wanted to tell you today. And this week on Wednesday, I'm not teaching a class, so I will meet you on next Monday. Okay. Any questions or any comments?
So I have a question.
Nice.
So for cardinality vertex cover in streaming setting, like, do we have a 2 approximation already?
In a streaming setting, in what? Edge insertion or edge deletion also? Edge insertion, yes, because you have a maximal matching, right? You take both endpoints.
Yeah, but maximum matching
Maximal
is
matching.
also.
You take a
Okay,
maximal
okay,
matching.
I see.
That's a factor
Yeah,
2 approximation, right?
Yeah.
So yes, for vertex cover you can do in, but for weighted vertex cover, well, you can. I mean, I don't know how.
Yeah, that's what you were going to show.
Yes.
Or is it even?
No. I was just trying to do vertex cover because it is easier to see. I'm going to do you maximum weight matching, and put this as a kind of exercise. Okay, for vertex cover. But I will do maximum weight matching because that explains. But this idea of weight function decomposition is slightly more easier for vertex cover. Unfortunately, I didn't have time to complete my discussion. So I will probably do a little bit more when I meet next time. But I would say that everybody should just have a look at local search tricks and techniques. It's quite cool.
Okay, yeah.
Okay.
Yeah, thanks.
Welcome. Okay, guys, then see you next Monday. Okay.